Okay. Good evening, everybody. Well, I can already start, right, Louis?
Yes, yes.
Yeah. Okay. Good evening, everybody. I'm very happy to introduce actually today Fred Chong, who is the Seymour Goodman Professor in the Department of Computer Science at the University of Chicago. That is in the United States, as we know. And he's one of the lead principal investigators of what is called the EPIC project, which stands for Enabling Practical State Quantum Computing, which is a nationally funded project, and in the University of Chicago has the ambition to become, actually is maybe already, but certainly wants to become a very strong player and maybe one of the leaders in the quantum computing world. So Professor Chong, you did his PhD at MIT, and then he was at the West Coast of the United States, at the UC Davis, and then he moved to Chicago. That was several years later. That was in 2000. I don't know exactly anymore. The 2005 years. I met the Professor Chong several times, several years ago. That when we started also in Delft working on quantum computing, and he's much more oriented, let's say, on the Qiskit, so the IBM kind of approach. The platform that IBM puts on the market is also largely used for the software. And being a computer scientist, he will be talking about the quantum algorithms and quantum software in general. So Professor Chong, you have around 45 minutes, give or take a couple of minutes. If you need more, that is fine. And at the end, so that is an open invitation to everyone. There's a chat in the stream, and if you have any question that you want me to pose to Professor Chong at the end of the session, you can write it down there, and then we'll see. In about an hour, we should kind of conclude the entire session. Okay, so Professor Chong, you have the floor. I'm going to mute myself. And if I see there's an important question, I may interrupt you, but basically you have the floor for, let's say, at least 45 to 50 minutes. Thank you.
Great. Thank you so much, Koen. It's my pleasure to be here, virtually, unfortunately. I wish I was in Porto, actually. In fact, ironically, a little over a year ago, Porto was the first trip I had to cancel because of the pandemic. I was on my way to Asplas in Lausanne, and actually had my family and I had planned to spend a week in Porto before going to Lausanne. And so it was the very first trip I canceled, and hopefully the first trip I get to go on again when the pandemic is over. So what I'm going to talk about today is maybe a little different from some things you'll hear in a series like this. I lead a project called EPIC, which Koen mentioned, which is a sort of a full stack software project. And really our goal is to bring much greater efficiency to quantum algorithms by making the software stack and the algorithms physics aware and optimize them at a very low level for the actual machines that they'll be running on. And we'll see that a little bit more today. Now, this project is with a whole bunch of great collaborators, and many of the ideas that I'll talk about today come from our work together. And this collaboration includes algorithms people at MIT, including Peter Shor, Aram Harrow, and Ike Chong, physicists at Duke, Chicago, and Princeton, including Ken Brown, Dave Schuster, and Andrew Houck. And then in the software stack, there are myself, Diana Franklin, and John Reppy. And then finally, we have some people in the quantum education area, which is Diana Franklin and Daniel Harlow at Santa Barbara. All right, let me just give you my sort of view, the computer scientist, computer architect's view of, why are we at an exciting time right now, right? And, I really got into this maybe, about 20 years ago, because, this quantum computation is the only technology that can fundamentally change what we think is computable as computer scientists. And, it's the only means that we can scale computation exponentially with the number of devices that we put into a machine, at least potentially. And that would allow us to solve currently intractable problems in areas like chemistry, simulation, and optimization. Also, as an architect, right, we've been dealing with this problem that Moore's law and Dennard scaling have been slowing down for quite some time. And this gives us a technology that will give us some sort of exponential scaling going into the future. And then finally, the study of quantum computation has led to interesting insights in classical computation, especially in areas such as chemistry, physics, and cryptography, but also leads to a healthy competition with quantum algorithms, between classical algorithms, and thus you get sort of quantum-inspired classical algorithms and just better classical algorithms as they compete with quantum algorithms. So why now, right? We're in this really exciting time that for the first time we have machines of non-trivial size, right? But the real problem with these machines is that they're noisy and they are error prone. So much of the work that I'll talk about today is how do we get the most that we can out of these machines through work in the software stack. And John Preskill really expressed this in an exciting way, which is we're at a historic time in science and technology because we have machines that essentially we can't simulate, and the only way that we're really going to understand sort of the algorithms and the machines and the power, the computational power of them, is to work with them experimentally. And so there's definitely going to be new science done in this time, this what he calls the MISC era. All right, so even though we're in an exciting time, we have some serious problems that we must address, right? So here we see, I plotted a couple of metrics of machine progress, the number of physical qubits in a machine on a log scale on the x-axis, and then perhaps more importantly, the error rate for a 2-qubit gate or operation on the y-axis, once again on a log scale. And what you can see is that over time, machines have moved moving from the lower left to the upper right, exponentially fast, in fact, right? The quality has been doubling every few years. But the algorithms that we would like to run on the upper right here are still pretty far away, and the machines have a long way to go. And so there's this sort of gap between the machines that we expect in the near future and the algorithms that we'd like to run. So, our project, the EPIC project, has this thing we call the EPIC goal, which is to develop algorithms, software, and hardware in a way that, in a co-designed way, to close the gap between the algorithms and devices by 2 to 3 orders of magnitude, which would be equivalent to about 10 to 20 years of progress of these machines moving from the upper left to the upper right, right? So the idea is pretty simple, and it's actually quite common in classical computation, where software efficiency can buy you time. And that's what we're going to do here. And it turns out that because the software stack, up till fairly recently has been not really that closely examined, we can really get a lot of efficiency out of it. And in fact, in the last 3 years, we found many optimizations that are, I'll show you examples that are very physics aware, which tend to be about 10x or so in greater efficiency, but up to even 10,000x. And in fact, I should be a little more precise. When we go back here, when I talk about efficiency, I talk about what I mean is a software stack that allows algorithms to run using fewer qubits, tolerates greater error, or uses fewer 2-qubit gates. Those are the metrics that will make it easier for us to run these algorithms on these machines. And so when I talk about optimizations that give us orders of magnitude in that regime, that's what I mean. And so, in fact, in those 3 years, there have been numerous things that we've come up with in this area, up to about 90 papers, 6 patents, and we even have a startup that has spun out to sort of commercialize this work. And we're also sort of trying to establish sort of this area of a systems view of quantum computation, which we would call a quantum computer systems discipline. And we actually have a textbook that came out, and there will be an edX class in this summer. And many of the things that I've talked about today have actually already been integrated back into commercial software, such as IBM Qiskit or Google Circ, or also Rigetti's software toolchain. All right. So here are some examples of what I mean, right? So we have a lot of things here in this left column, which are examples of different optimizations that we've worked on, from minimizing the number of measurements in VQE for quantum chemistry, to compilation that goes directly to pulse control instead of machine instructions, to different kinds of mapping and scheduling, to 2.5D, 3D architectures that give us better efficiency, and things like dealing with crosstalk. And so there are quite a number of things, and I'll give you a few examples today in the time that we have. And then we also have quite a lot of other efforts which have to do with sort of building this community and this area of quantum computer systems in terms of software that we distribute, courses, curriculum, and tutorials have reached really tens of thousands of people. Okay, so in the time that I have today, I'm going to go over these 6 examples. And it's going to be a little fast, so feel free to ask questions, or at the end we can talk more in depth about some of these things. But I really just want to give you a flavor of the kind of research that we do, and just intuitively how it is that if we sort of break traditional abstractions in classical software that we would be accustomed to, that we can get much greater efficiency. All right, so the first set of work that I'll talk about is something that we call NoiseAdaptive Compilation. This is a series of 3 papers that we did with Princeton. And it really sort of changed the way that quantum machines compile programs to their devices. All right, so this was motivated by an observation that Prakash Murali at Princeton made, which is that quantum hardware, especially IBM's quantum hardware, varies significantly day to day. And IBM, in fact, calibrates their machines every day, and they publish that data so we can see it. And you can see that here on the upper right, the quantum bits on the machine, the physical devices that represent the quantum bits, vary significantly day to day. This is the y-axis is a sort of a metric of the qubit quality. It's has to do with their decoherence time. And so lower is better, right? Or no, higher is better, sorry. Higher is better. And what you can see is for the different qubits on the x-axis are different days. Over 25 days, you can see they vary quite significantly. And not even the same qubit is the worst qubit on different days, right? And so you see that there's a lot of variation. And then, in fact, if we look at here, this is a 2-qubit operation, a controlled knot between 2 different pairs of qubits. You also see that the pairs of qubits vary significantly, and that's basically the coupling between those pairs and how well they work together. And here I plotted on the y-axis the gate error rate for different days. And so lower is better. And you can see that sometimes some of the gate errors vary quite significantly on different days. And once again, it's not even the same pair that's the worst every day. All right, so what we're going to do is we're going to break the abstraction that you normally would compile a program for a particular architecture, have a binary that you can run at any time on any machine of that family. So what we're going to do is we're going to target a specific instance of an architecture, specific machine, on a specific day even, right? So very different from our traditional sort of classical model of compilation. Now, here on the left, I have an example of a quantum circuit. If you're not familiar, the P0 through P3 are qubits. Time goes from left to right. The boxes are single qubit gates. The little dots with the little plus in the circle, that's a controlled knot, so that's a 2-qubit gate. And the little meters on the right at the end are when we measure and get the result. Now, if you take the IBM software flow that used to exist before we did this work, you would get a mapping on the upper right, right? So on the upper right, you can see that the P0 through P3 are sort of mapped so that they're very close together. And that's what the IBM software tries to do. It tries to minimize communication by keeping the qubits close together on the machine. So that's the physical machine there on the upper right. What we did was we did sort of the same thing on the lower right, try to keep things together, but we try to avoid the red X's, which are bad couplers or bad pairs of qubits on that day, and the gray circles, which are bad qubits on that day, right? So essentially what we did was we encoded these as optimization constraints in an SMT solver and tried to balance minimizing communication and avoiding bad parts of the machine. And the result was about 3x better reliability, as high as 28x for some different applications. And this did so well that it's now integrated back into IBM Qiskit. So now the default optimization in IBM's compiler will do this noise-aware mapping. And this really just changed how quantum programs are compiled. And the key was to break this compile once model, right? And be very dynamic and incorporate the daily information. All right, so now I'm going to go on to another example where we're going to go even farther in breaking abstraction, right? So now what we're going to do is we're actually going to break the abstraction of machine instructions. And in fact, we're going to compile to microwave control signals instead of machine instructions. So what are we going to do here? So on the left here is a piece of a quantum circuit, much like the previous example. And on the upper part of this diagram is the path that you would normally take. And what you do is in the IBM compiler, for example, you compile to something called OpenQASM, which is a quantum assembly language, which is essentially quantum gates. And then each one of these gates then gets translated into microwave control signals, which you can see in the upper right, right? And so you see over time, what we're doing is we're hitting the qubits with different signals, and it accomplishes these 4 instructions here that you see in the quantum assembly. Now, if instead we take this function and we treat it as a block with an input, set of inputs and a set of outputs, and you think of it as a start state is the input and an end state, which is the output state, we can actually feed this into a gradient ascent optimizer, which finds the shortest pulse sequence that allows us to implement that entire quantum function. Now, this is very expensive, but it creates a much simpler and shorter pulse sequence, as you can see in the lower right. And in fact, what happens is we get something that's about 2 to 10 times faster for different quantum benchmarks. And what's happening is you can think of this picture on the right, where we're going from the start state to the end state for a particular block. And you can think of the gray arrows as what would happen if you did it one quantum assembly instruction at a time. You would take sort of an indirect path. But what you're doing here is you're using classical computation to find a set of control signals that get you from the start to the end as quickly as possible. And in the physics world, they call this optimal control, which is usually used for single qubit and perhaps 2 qubit operators, but we're using it for a large block, which is expensive. So of course, as I said, it's great, but it's expensive. It can take hours to compile a program before we can run it. And this can be a pretty serious problem if we have these new hybrid algorithms where we have a quantum kernel in an inner loop that's run many, many times with a classical supercomputer in the outer loop. So I'm going to move on to our next work where we make this, we adapt this to this situation, which is challenging. All right. And so this is the situation where things like quantum chemistry or optimization algorithms like QAOA, what you have is what's called a variational algorithm, right? And the variational algorithm is a hybrid algorithm which runs on both classical hardware and quantum hardware. And you're going to loop thousands of times calling the quantum hardware. And in this case, you have a circuit such for quantum chemistry, such as on the right. And what happens is you could see these operators, these single qubit rotations, which are in red and in blue, they change, their input parameter changes every iteration. But actually what's key here is they're the only things that change. Much of the circuit remains the same. So what are we going to do? We're actually going to use something called partial compilation. What we're going to do is we're going to compile each one of these blocks that's dependent upon, as it turns out, a single parameter. We're going to figure out most of the compilation ahead of time, and then at runtime, when we at each loop, we'll adjust that compilation for the new input parameter. And what we get is we can preserve about a 2x speedup in these algorithms, but we could compile about 10 to 80 times faster than the previous method that took hours, right? And so take these two things together. The key was to break the abstraction of machine instructions and practically target pulse control. And pulse control, I think, is going to be a really exciting tool as we go forward in getting the most out of these machines. Now, I will take a step back that, one of the things we're doing is we're breaking abstraction and throwing a lot of complexity into the software tool chain. And we can do that because machines are small and programs are small. I'll talk a little bit more about this later as we get to the end of the talk, right? Where's this trade-off going to fall as we go into the future? All right, so I'm going to, here's our third example. So our third example is actually something quite different. You can think of it as a quantum garbage collection, right? So we're going to manage qubits. And what we're going to do is we're going to try to minimize the number of quantum bits we use by figuring out which ones we can reuse in a computation. And it's, like I said, it's similar to this idea of garbage collection. But in quantum programs, you must uncompute part of your work in order to reuse a quantum bit, right? So it's essentially, if you just reuse a quantum bit, you will likely corrupt your result. And what you have to do is essentially undo the relationship between any temporary qubits with the result that you care about. And so we can see this here. So here's an example circuit on the left. And on the right, on the upper part of the right, you can see that what we're going to do is we're going to uncompute part of the circuit to get back something. So we go here. Let's see. Right. Okay. So the bottom one is more the intuitive thing is what you have to do is you have to uncompute this U of F, right? So I have a nested function. The U of G is a circuit block. Inside, there's this little U of F block. And what I'm going to do is I'm going to take that U of F and I'm going to uncompute it. And you can see that there's a part that says reclaim. We can get that qubit back because now we've undone the computation that it's involved in. And it turns out that if you have a recursive function like this, there's a sort of interesting, what we might call the eager approach, where we can uncompute earlier and get back that qubit earlier. But what's interesting is that later we have to recompute the thing we uncomputed when we try to uncompute the outer function. It's sort of a interesting mind-bending thing that recursive uncomputation makes a lot more work, but gives you qubits back sooner. So there's this actually compiler strategy where we have to decide whether to be eager or lazy in our garbage collection. And it's basically a trade-off between number of qubits you get back and number of gates that you invest in getting them back. Now, we actually designed this mechanism for future fault-tolerant machines that have much more reliable gates because we're going to invest gates to get qubits back. And right now, mostly gates are the dominant factor in the errors in our machine. So we don't want to perform a lot of extra gates. But much to our surprise, even for current NISQ machines, we're 50% more reliable on these machines if we use this approach than we don't. And we were surprised because, as I said, extra gates cause errors. But it turns out that uncompute saves you communication sometimes. And so I'll give you an example here on the right. On the right, this is an IBM machine. Now, let's say that you need a new qubit to use in your program at location 24. And what can happen is, okay, I need a new qubit, but the only way I can get it, let's say the new qubit is, I have a free qubit that isn't being used at location 50. And the way we get it to location 24 is we actually perform swap operations and move it from 50 to 24. Those are the red arrows. The swap operations are actually 3 C0s, so it's 3 gates for every red arrow. It turns out that it can be cheaper to uncompute in place, get qubit 24 back and use it in place, that's that little green recycle arrow, than potentially moving a new qubit from far away. So that's where we actually get 50% or a factor of 2 in near-term machines. But on future machines, we expect to actually get a 10x benefit when gates become cheaper and when we have things like error correction. All right, so that's the reuse result. A couple more examples. Here's an example which is very different. We're actually going to break the abstraction of binary computation. So instead of using a qubit, we're going to use what's called a QTritz. And the simple thing is, just like in the previous work, we were worried about having to use too many temporary qubits or too many qubits as what we call ancilla. Here, we're actually going to use a QTritz, which can store more information, to take the place of an ancilla. So we're going to take actually what was a data qubit and overload it with and use it also as an ancilla. All right, so this idea of binary versus ternary computation has been around for a long time in classical computation. And in fact, in the classical world, we haven't really gotten a lot of mileage out of ternary computation. And I think a lot of that is because in the classical world, you have some finite amount of signal, say 0 to 1 volt. And you can either choose to break that up into 2 values for binary computation or 3 values for ternary, but you really still have the same amount of signal. And what you're really doing is you're squeezing your noise margins and hurting your signal to noise ratio. But in the quantum world, here on the right, you can see for a superconducting device, you have these different energy levels. And what we do actually is we truncate the representation, and we just use the lowest 2 energy levels to represent the 0 state and the 1 state. But in fact, there are a lot more energy levels we can use. And so in some sense, there's more signal. And so it makes a little bit more sense in the quantum world. But it is also the case that the higher levels have more noise. So we have to model some of the noise effects of this. And it's also the case it's a little bit difficult to measure 3-state QTritz versus qubits. So in fact, you'll see that in our technique, we actually only use the QTritz in the middle of the circuit, and we never measure them. We go back down to qubits by the time we get to the end. So I actually don't have time to show you all the circuits today. We can talk about that more offline. But what we're doing is we're basically using fewer devices, the same devices, to represent more information, because we have 3 states instead of 2. And we get actually up to a 70x reduction in the number of devices you need to support a program by leveraging this extra state to represent ancilla. There's been quite a lot of interest from hardware providers in this kind of technique. On the right here, we actually show an experiment we did recently that implements QTritz using the pulse interface on IBM's machines. This is a simple 3-state counter. You can see the 0, 1, and 2 state, and we just cycle between them. And we're able to experimentally show that this is feasible on these devices. Actually, even though the machine wasn't designed for it, the pulse interface is just flexible enough that we can actually do this. And so I think there's a lot of promise here, and we're going forward, trying to implement this on real machines. Rigetti recently, I think at APS, had some results where they did some QTritz work using their pulse interface also. All right, 2 more. Sorry if this is a lot at once. So here is a different kind of project where we actually looked at a new technology, which is superconducting technology, but actually that uses resonant cavities that actually form pretty good quantum memories. And we're actually able to build sort of a 3D, or what we call a 2.5D architecture, which is a great match, as it turns out, for surface code error correction which is laid out on a 2D sort of topology, right? So what we do is actually we take the traditional surface code, which is a 2D code, an ensemble code that you can see on the left. And instead of building it out in, for example, 4 blocks here on the left, we build essentially a single block on the right, and then we hang a memory off of each one of those qubits, which in this case are transmons, and the memory is a resonant cavity. And the cavity can store many qubits, let's say 10 qubits or so. So what we can do is we can have a stack of 4, or in this case, or actually 10 or 11 or so, surface code tiles. And so we can build a much smaller device, which can actually simulate this larger 2D topology here on the left, right? And you can think of this as virtualization, right? So you have physical qubits, which are at the top. You have memory, which basically backs those virtual, the virtual tiles that you can think of. And each tile is essentially a logical qubit. And so what we get actually is not only a virtualization and compactness. It turns out that there's something that, which is you get random access of any layer in the memory, okay? And what that allows you to do is it allows you to interact any 2 tiles or any 2 logical qubits in the system very easily. And in fact, you can do this thing, the controlled knot, in what we call a transversal way, which is it's bit parallel across all the physical qubits. And that is not true when you have just the 2D topology. And it turns out it's about 6 times faster than if you only had a 2D topology. This 3D gives you this essentially communication advantage. Now, the compactness does cost you something. You basically have to do loads and stores to get in and out of the memory, and that has some error associated with it. It's pretty fast and pretty low, the error, but it is essentially you're serializing the computation a little bit. And in fact, we can serialize even more. So this is what the topology looks like normally, which is essentially the first picture I showed you. But what we can do is we can actually multiplex or share 2 of the qubits in this topology, or there's some, so what we do is we take this and we smash this topology like this. And what it does is it essentially gets rid of some of the ancilla, and it shares the ancilla with one of the data qubits. And what that does is it serializes the error correction. It saves 2 times the number of transmons or qubits at the top of the 2D topology. But it's 2x slower, right? So we pay speed, but we get space. Now, overall, what happens is, we can look at what the error correction power of this architecture is in its different versions. And we did this with some error simulation. And what we get is this, okay? So this is a standard, what's called a threshold plot, right? So what you can see is the error rate is on the y-axis, and that's the logical error rate. So after you do the error correction, how much error do you have? And on the x-axis is the error rate of the devices. And when you go from left to right, the error is getting worse, right? And so what happens is there's a crossover point, right? Where you can see that the error correction starts making the error better as opposed to making it worse, right? Because the error correction costs you gates, and you need the reliability of the gates to be reasonably good before you can get some advantage. And this threshold on the top left is about 1%. And that's for the native error correction code in a 2D architecture. And all these other versions, oh, actually, it's not the top left, it's the far right. That's the baseline, okay? And all these 4 graphs on the left are different versions of our architecture, where the bottom right is the most compact. And you can see you sacrifice about 0.001 or 0.1% of your threshold which means you need a slightly better device to make this work for a compact architecture, but only slightly, right? And so what this shows is that this architecture is comparable to the original architecture, but much more compact. In fact, what's exciting about this architecture is it gives you a 10x reduction in the number of transponds you have to build. It's faster. It's about 20% faster using this transversal C0. And the coolest part is this thing on the bottom, that we could build a machine with only 11 transponds and 9 memories, these cavities, which is perfectly buildable right now, that could actually support 10 logical qubits. And this is quite like an order of magnitude more than you would expect from any machine we could build in the near future. So I think that's pretty exciting about this work. All right, so I've got one last thing. This work is pretty interesting. This work is actually going to show you that by being careful in our software design, essentially by managing the noise in a machine using software, we can build a much simpler machine which has equivalent performance with a much more complex machine. And this is really relevant because if we look at machines that are out there, they actually fall into these different categories. So we'll take a look at this. Okay. So we're looking at the problem of crosstalk. So here's an IBM machine. And if you run two 2-qubit gates at the same time in the black rectangles between 1 and 2 and 6 and 7, it turns out the error rate of those gates is 10 times worse because there's crosstalk between the 2 gates. And that's because there's a connection between 1 and 6. So the 2 gates resonate with each other and produce errors with each other. So what we're going to do is we're going to look at building a machine that has qubits in which you can vary their frequency, but connections between qubits that are fixed. That is, the qubits are always connected or not always connected. This, incidentally, is the way that Righetti's machine works. We're going to compare this to the IBM machine, which is much easier to build and manufacturable, which is sort of IBM's approach is to choose a technology that's very manufacturable. It has a fixed qubit, so the qubit can't change its frequency, and a fixed coupler. And the way the IBM machine avoids crosstalk is it basically serializes the computation. It doesn't allow qubits or gates to be in parallel if they're going to have serious crosstalk. But so it turns out that this machine is about 13 times more reliable than an IBM machine if we can tune the qubits and use our software. But what's perhaps even more interesting is with our software, we can make our machine about the same as the Google Sycamore machine, which has both a tunable qubit and a tunable coupler. And the Google machine is much harder to build. Google has a 53 qubit machine. And what's interesting is they had a 72 qubit machine a couple of years before that one. And you might wonder, why did the progression go from 72 to 53? It's because a tunable qubit, a tunable coupler is about as hard to build as a qubit. And their machine really is something like 3 times as many qubits as you think, because every qubit has 2 tunable couplers attached to it. So essentially, it's like you had 159 qubits instead of 53 in that machine. And so that's just gives you a sense of how hard it is to build that machine. So what do we do? What we do is we actually take a 2-step approach. So we take the physical machine, which is this thing we represent with the connectivity graph on the upper left, and we simply do a graph coloring so that the idle frequencies, the qubits, stay in frequencies that are different from each other if they neighbor each other. And then what we do is we take each program that we want to run, and we take each set of parallel operations in every time step, And we produce what's called a crosstalk graph for that little piece of the program. And then we do graph coloring on that. And then we use that graph coloring to figure out what frequencies to implement the different gates in the system, right? And that allows us to essentially avoid crosstalk in a very nice way. And it's also the case that this crosstalk graph, since it is since it's per time step for a program, it's not too big and it's tractable because, of course, graph coloring is a hard problem. And so the result is something like this. Okay, so the blue bars are the IBM-like machine with fixed qubits and fixed couplers. And higher is better. This is program success rate for a whole bunch of different benchmarks. And you could compare that to our sort of most sophisticated approach, which is the red bar, which you can see is significantly better than the blue bar. And then you can see that the red bar is similar in general to the green bar, which is the Google-like machine, right? And so that's the general result, right? Much better than everything fixed and pretty much as good as everything dynamic, right? Tunable, but much easier to build. All right, so let me wrap up. You know, all of these examples that I've shown you really are an example of, you know, a very vertically integrated sort of domain-specific software stack that connects the program to the hardware level. And so here on the left is the specific thing we used for this crosstalk mitigation, but all of the examples pretty much are this sort of deep, you know, domain-specific software that connects the physics of the machine to the program. And really, this is a, you know, an ongoing trend in, you know, sort of computer systems and architecture in general, this domain-specific system design, right? Very vertically integrated software stacks. And it's analogous to things like the TensorFlow stack, right? And it was highlighted, you know, in a couple of years ago by Hennessy and Patterson in their Turing Award lecture. You know, this is the thing of the future, right? That domain-specific design is how we're going to get efficiency out of our systems. And quantum systems are really just a really extreme version of that. But let me end with something I mentioned in the beginning, right? So in the beginning, I talked about the gap between the algorithms we want to run and the machines that we have today. There's another gap which is interesting to think about, which is, you know, we're doing research right now and building software stacks for small machines of 100, maybe up to 1,000 qubits, and we're breaking abstraction and doing very low-level optimization. Now, what's going to happen when we get into the future, into the sort of fault-tolerant domain where we have 100,000 or even 1 million qubits, right? Will the lessons that we learn today and the approaches that we take really carry forward as we go to the future? And you can think of it as, you know, quantum computation is similar to, you know, classical computation as it was in the 1950s. And as we went forward in classical computation, you know, bits became essentially free. Instructions were, you know, essentially infinitely reliable almost. And so we became much more much less resource sensitive, right? But even classical computation is backsliding a bit now that we, you know, have very small feature sizes, we have variation in our systems, and we even start having errors, and we have energy constraints. So I would argue that, you know, it's, maybe I'll be wrong, but, you know, it's hard to imagine a future in which quantum bits will be free and quantum gates and bits will be, you know, infinitely reliable. I think we'll always want to, at least in terms of system software, be somewhat physics aware and, you know, get the most that we can out of unreliable systems. So, you know, let me sum up, right? You know, I started with this idea that, you know, quantum computation is a really historic time. And, you know, I would argue that, you know, what we really have a shortage of are people who have a perspective of a systems view of these machines, you know, that are trained in both the sort of computer science and physics of quantum computation. And we really need to develop such a workforce. And we're really trying to, in our project and at our university, develop this discipline of which I sort of gave you many examples today of quantum computer systems. And so, as I mentioned, we have this book, and we have some edX courses coming out And I really, we've really been trying to get people interested around the world in this kind of research. There was a lot today. We have this, EPIC has a very extensive website, which you can follow some of our work if you're interested in some of the details. Thanks a lot.
Okay, thank you very much, Fred. Normally you will hear an applause of the people listening, yeah, but I will just applaud myself for you. Yeah, I do have a couple of questions that I would like to ask. There's one thing that kind of struck me in your entire talk is that you're very superconducting oriented, because you mentioned Rigetti, Google, IBM. There's also Alibaba in China. It's all superconducting, and we know there's so many competing quantum technologies with each other. Yeah, I don't know whether Intel would be so happy to see that you're only looking at superconducting, right? Because they're moving more towards semiconducting, which from their point of view is understandable. So there is of course a very technology directed in the way that you're approaching things. Yeah, if you talk about even this transversal CNOT in this quantum memory, that's very specific for, let's say, superconducting kind of things. And so how do you view the current work, which is extremely interesting, because I was fascinated to listen to you, yeah. But how do you see that if it suddenly becomes ion traps? Because I don't know about the US, but in Europe, in Northern Europe, it's more photonics, and then you have a superconducting, semiconducting, and ion traps in Austria. So it's very varying. And then what is useful from what you're proposing into other quantum technology domains?
Yeah, no, that's a great question. And I will say, in this sort of short talk where I crammed in a lot of stuff, I'd maybe give you the wrong impression that we're so superconducting oriented. EPIC is actually technology agnostic. Ken Brown, for example, on our team is a trapped ion guy. And we actually do quite a lot of trapped ion work. The QTritz work, for example, was also modeled with trapped ions. What you tend to see in my talk is a little bit of a bias in my community for empirical results on real machines. And it just is that, IBM machines are the most available right now. Yeah. And that's starting to change, right? In fact, we're just about to release a benchmarking effort in which we run on IBM, IonQ, Rigetti, so we're starting to have access through, for example, Amazon Quantum Cloud and Microsoft Azure Quantum Cloud to different machines. But so part of the bias you see is that, in fact, I sort of focused on the award-winning papers, and the award-winning papers are the ones that people like because we ran it on real machines. We have a lot of simulation work on different things. And so, in fact, much of what we do, has to do with communication, with topology, with control and noise. And it tends to generalize to a lot of these different machines, perhaps less to photonics, I would say. But, we have worked with Intel. We sometimes do model their systems, although, it's a little bit less mature than, for example, even our trapped ion models. And now we can actually, access IonQ machines and actually run experiments on them. It's a bit of a reflection of the state of the art and the availability of those machines. IonQ, for example, we can get to the machines, but they don't expose pulse control yet. So we can't do any of the pulse control work on their machines except in simulation. We can simulate academic trapped ion machines. But in general, in fact, just a week ago, I gave a talk at a funny workshop at ASPLOS called NOPE. NOPE is about negative results, opportunities, perspectives, and experiences. And I gave a sort of 20-year retrospective on our quantum work. And actually, a surprising amount of the work that was, we tried to make technology agnostic, did generalize to other technologies. 20 years ago, we didn't know this is how systems would look, right? But we were looking at things like communication and mapping and parallelism and control, and all those things are fundamentally important from an architectural point of view. So, but I'm glad you asked that question, because definitely if you, from my talk, it would seem like we just care about superconductors.
Okay, thank you for the answer. I do have a question from somebody, Mr. Oliveira, is Could you please elaborate a bit on the possible advantages or disadvantages of using these QTritz as a kind of 3 levels logic? So what are the positive or negative side effects of these things?
Yeah, absolutely. So like I said, the 2 big disadvantages of QTritz are, one, when you use a higher state, there's usually a higher probability of error, right? And so theoretically, that essentially scales linearly. So with the photon number of the energy of the state. So if you use a 2 state, then you essentially, have double the error of the 1 state. And so we have a model of that error. And essentially what we do is we try not to use the 3rd state very often for very long. And then the other thing is it's harder to discriminate 3 logic levels than 2 when you do measurement. And so experimentalists most of them don't like to measure QTritz. And so what we do is we have a circuit that's qubits in and qubits out. But in the middle, we take some of the qubits and turn them into QTritz. And we essentially use that 3rd state as an ancilla state. And it's a little bit, there's a subtlety if you look at the papers and how we do it, because if you had Q-quartz, if you had 4 states, right, then it would be exactly equivalent to having both a data qubit and an ancilla in one device. And then it would translate directly. But we had to be a little clever to use only 3 states. So it's like, a little bit less information. So that's, and then we have results in the detailed papers as to, basically, because we're able to, in the same number of devices, have a more efficient sort of lower circuit depth. Because basically, if you don't have enough ancilla, your circuit becomes longer and the depth becomes longer, the error becomes higher. So the advantage in circuit depth basically outweighs the disadvantage in higher error rate when you go into the 3rd state. And so that's the technical trade-off. And you can use QTritz for other things, but this QTritz for ancilla in the middle of the circuit seems to be the most advantageous and seems to be the thing that's caught the most attention of the experimentalists because, of course, experimentalists have always known about QTritz. They just didn't think they would really be useful, actually.
Okay. I have another question actually from someone who's doing his PhD with me right now. Yeah, he said, as a quantum algorithm designer, can I design a quantum computing approach of an application in a naive way? So that means hardware agnostic, and then the tools from let's say Qiskit that will take care of optimizing it in the compiler passes. So is there a kind of compiler solution you can abstract away? That also is very close to another question that I wanted to ask. I define things much more now in perfect qubits, yeah, so that there's no decoherence, no error rates, and yes, we need to translate that in, say, you use the open quasum or another kind of quasum, yeah. So it's basically along the same line that this question can be interpreted.
I think most of the techniques I talked about today are transparent to the user, right? They're really at the system level and lower in the stack, and so I think it is true that you can be platform agnostic and fairly agnostic to, think about ideal qubits at some level. That's for most of the work. I think there is some views, so we look for 3 or 4 orders of magnitude in efficiency, and probably 1 order of magnitude comes at the application level, right? Yeah. We could probably get a lot of it, at the system level. But for example, I didn't talk about it in this talk, but the work in which we reduce the number of measurements necessary for quantum chemistry, that requires a modification to the algorithm, right? So we do some work at the algorithms level, but I would say most of our work is transparent to the user and to the program.
Yeah. Okay, thank you very much. I think we're 1 hour 10 minutes, so I think it is a good moment maybe to conclude this session. And we thank you very much again, Fred, for the very interesting talk that you're giving. We wish you good luck, and hopefully that we get the chance to meet each other again in conferences or wherever it's going to be. Yeah. Absolutely. So
yes, yeah. I hope to come visit.
Yeah. Okay. Very good. Okay, thank you very much, and thank you again for your excellent work, and we'll see each other again in the future. Thank you very much.
Definitely, it was good to see you.